Okay, so it's top of the hour. Thanks everyone for joining. Today this talk will be about container attached storage. A little bit about my background. I've been in storage for roughly 10 years or something. Mostly worked on software-defined storage systems on a variety of platforms. And to be honest, I was actually looking into doing something else than storage, and then containers re-happened, with the emphasis on re-happened because it's not really new. And here I am talking here today to you guys. So before I continue, I want to point out that a central component throughout this talk is containers and Kubernetes. So a lot of what I'm going to say today won't work with Kubernetes, without Kubernetes. This is not about PVs and PVCs, so don't worry about that. But it is an integral part. And the genesis of the openEBS project was around the idea of providing a platform for stateful workloads in a cloud-native environment. And if you look into how these applications are built, we believe that it justifies to rethink certain things in the way that we do them in storage. So, but before we go into that, oh, hold on, next slide's not coming. There you go. As we started to develop on openEBS, we noticed that there are some things happening at the same time. And there is this movement in parallel, let's say. And one thing is the people, so the actual end user that uses the storage in cloud-native environments. And these people are the ones that develop, configure, deploy, and operate these systems in production. The software itself, obviously, it's not the same as it was 10 years ago, but there are certain things built into these cloud-native applications from the get-go that may result in doing things a little bit differently, again, from a storage aspect. And lastly, hardware, obviously. There's a lot of talk about these type of things, NVMe and SSD, during this conference. And so, we really want to try to figure out how we can exploit these new things. So, combining all of this together, for me personally, it made me a little bit more excited about, hey, we can actually build something nice. So, one thing, as we started to talk to these people that we learned from the past, and one thing that stood out specifically is that applications have changed and somebody forgot to tell storage. And when I say apps, I implicitly mean this client-server model that is almost default. So you access something on your phone, that's the client, and the service runs in the cloud. And storage people, and I am not an exception to the rule, but we tend to think from the device up, right? So we have our precious, non-volatile whatever, and that's the coolest thing out there, and we try to make that available to the end user, but we really try to invert that and see, okay, what is it actually that you guys need in this cloud-native environment, and what can we do to help achieve that job or goal? So let's look a little bit into these things that have changed, or at least I could put a huge list on this, but one of the most important things is that cloud-native applications are distributed systems themselves. And they are not afraid to use distributed algorithms like Paxos or Raft. Nobody flinches if they use these applications or these protocols in the core of their applications. There is this rise of new cloud-native languages, Metaparticle, Ballerina, and if you look at how these applications are, or how these languages are built, is that they kind of import containers and then connect containers with the syntax, and it's kind of weird when you initially see it, but when you're developing these type of applications, it might actually make sense. And the other thing is that the applications are designed to fail across DC, so this is a built-in thing. They assume for it to fail, and it's not just across nodes, as I said, also DCs, but also regions and even providers, and it needs to be multi-platform, multi-cloud, multi-hypervisor, multi-anything. Databases, there are a lot of these non-SQL or key value stores databases out there, and they all have a form of load distribution, scale out, sharding, or what have you. And the final piece that we observed is that data sets of the individual containers themselves are relatively small. So you will certainly see every now and again a container that has a petabyte in terms of storage, but in general they are relatively small. And this is because the applications themselves are distributed by nature, right? So you don't end up with these heavy storage capacity type like workloads. So to sum up that a little bit is that data availability and performance is not anymore exclusively controlled at the storage layer, where typically you had this monolithic application that was running hunky-dory on your system, and then you virtualized it, and then, okay, that kind of worked. And if you wanted to scale the performance of your application, what you typically did is you add more shelves to it, right? Or you did a forklift upgrade by swapping the head and changing it for another one. With a scale-out system, you would add nodes, or you would add nodes with faster media. But all in all, it was controlled at the storage layer, and if your storage layer went down, you had a huge problem. So there was a lot of money involved in building these reliable storage systems. So software-defined came along, didn't really change all that much, software-defined storage, I mean. Perhaps what it changed is the cost model a little bit, where the initial hit on buying the system was a little bit less, but keeping them afloat was a lot harder because all the cool things that the vendors handled, like blinking a LED, that did not always work. So the other aspect is the people. As I mentioned, the DevOps persona, so openEBS is very much targeted at these people. They deliver fast and frequently, and rumor has it if you work at GitHub your first day, they tell you you will actually write something that goes in production today. So there's a little bit of pressure if you come there. I don't know if it's true, of course, but could be a typo, doesn't really matter, but you really need to deploy something in production. CI/CD pipelines is something else. Every commit kicks off a complete build. Pretty sure you guys do that one way or the other yourselves. Blue-green deployments is something that is very common these days. I'll go over an example of what that means. Software delivery obviously has changed a lot. I usually call it tarball on steroids, so it's not just the binary, but also the execution environment defined in YAML that comes along with the application. And declarative intent is also a thing that you see in these cloud-native environments, and everything is version controlled, and the whole infrastructure is version controlled through things like GitOps and ChatOps and whatnot. And Kubernetes is, I think we could consider that to say that it's the unified cross-cloud control plane. So it basically allows you to do from private, public, different clouds. Kubernetes is like basically the cornerstone of it all. So hardware storage trends, this is probably something that you guys perhaps even know better than I do. But one of the things that we observed is that storage vendor limitations, which whatever storage vendor it is, some of the limitations of that particular storage system bubble up in the application design. And that makes it really hard to write code that is optimal if you move it from one cloud to the other, or from private to public, or vice versa, or even have this hybrid model where you have something private and something public. So there was a lot of friction we saw when talking to these people. Very rudimentary things. I don't do CIs when I do backup. Well, don't do backups while I'll do CIs. These typical things create a lot of friction. Storage administrators go bananas. All those workloads coming left, front, right, and center. They need LUNs, every day, every minute. And one of the things that stood out to me is one of our friends who was working at a website that allows you to book hotels. If you think of the two top ones, you probably have the 50% chance of hitting the right one. And he basically said, we're done with these storage systems. They're too complex. They have their own manual. It's all this, it's all that. We simply use direct attached storage using NVMe because nothing goes faster than that. A persistent DIMM. Sorry, yeah. So increasing core count creates also new challenges. Well, maybe not so much challenges, but concurrency primitives are built into languages these days. So as these developers write these concurrent programs that are falling in their lap, they don't have to spawn a thread. They just use channels or something like that. And so they create very concurrent software, maybe not even intentionally, but that requires also some stuff at the background. So, this picture, I think you guys have seen it. I haven't collected this data myself. This actually lives in the GitHub repo. I find it very interesting, but it clearly shows the trend that the core count goes up, which ties back into these concurrency primitives in languages, and the frequency creeps up a little bit, but doesn't change all that much. The cool thing is, though, is that that is a perfect match. If you look at how NVMe at the core works with those queue pairs and all these type of things, RDMA, and a 1U server, I don't know if the amount is still correct. I grabbed this picture off the internet, but there's actually a physical box in the lobby if you have seen it. But you know, it's kind of amazing that this lives just in 1U box, right? So the other thing is that with containers, you can actually control very granularly which container gets access to what. So if you, I believe you could put 24 cores or 48 cores in this system. You can actually, through containers, decide what resources should be dedicated to storage and what should be dedicated to the application, right? So it is very flexible. Makes it also very hard, to be honest. So, but you know, one does not simply create a new storage system. As I mentioned, I've been in storage for 10 years, so I know how very, very hard it is. So we didn't really want to create a new storage backend per se, and we also are not talking here about we've found this new B3++++ algorithm that's even faster than all the previous ones. But we do see an opportunity to innovate in this space if we keep the focus on cloud-native applications. So the question that we asked ourselves is what if storage for container-native applications was itself container-native? So actually put the storage controller in a container and make that, you know, like a first-class citizen of the DevOps persona toolbox. So it kind of looks like DAS, right? But not really. So we thought about CAS and then referred to it as container attached storage. I picked up the SNIA dictionary, I think is what it's called. CAS is not in there, so maybe next year, who knows. But I'm well aware of the fact that it's also used for content addressable storage, but that's a completely different ballgame. So based on these conversations and these limitations that we found by talking to these people, we put some design constraints on the system that we wanted to build. And one thing that we did not want to do is build another distributed storage system. There is a plural of distributed storage systems. Building these systems is really, really hard. As I mentioned, cloud-native applications are distributed systems themselves, so putting distributed on distributed is an operational nightmare waiting to happen. And obviously, what's most important is small is the new big, because those data sets are relatively small. Cloud-native versus cloud-washed, I want to point out this a little bit. What it means to us is that you don't just pick up your application, put it in a container, and say that you're cloud-native. There's more to it than that. So the idea is that we have a per workload storage system using declarative intent by the developer, so the developer has full control, no more friction between the departments and these type of things. Reduce the blast radius, so if one of the microservices goes down, not the whole application goes down, or even worse, the whole department of the company goes down. Obviously runs in containers for containers, so this implies that it has to be in user space. It's not a clustered storage instance, rather a cluster of storage instances. So small but fundamental difference. So how does this look a little bit? So on the left-hand side is what you typically had Kubernetes 101 when it initially started out. There was no state. So these were all, let's say, web servers, and you could scale them up and scale them down. There's actually a command called scale, and you enter a number and let's say 5, and it would spin up 5 instances and so forth. So now we want to basically do the same thing, but stateful. Again, based on Kubernetes, leveraging Kubernetes, through YAML, which the developers use to declare their state. And then we would provision next to the actual container an additional container that contains your data. So there's a lot of contains in that sentence. So the challenges and the solutions that we think that we solve, sum them up. So small working sets, as I mentioned, and this allows us to keep the data local. Local doesn't necessarily mean that's physically on the same node, but ideally that's what you want to achieve. Ephemeral, so some workloads that are stateful don't necessarily need to be preserved if the container is removed. And these type of storage systems are also very familiar. And in our case, the storage lives as long as the pod. So if you clean up the pod, the data is gone. You don't have to do that, by the way, but that's an option. Scale by end, just add more end containers. Mobile workloads, and we can follow the workloads. Obviously, there is some inertia involved. You cannot just instantly put data from one node on the other node. But as I mentioned, the working set size is relatively small. That makes it feasible to do some form of replication in the background and then move the workload when it's done. The DevOps is responsible for the operation, so it's just another microservice to him. Cloud lock-in. Some say that cloud is the new proprietary. Some people go out all ballistic on AWS and use everything what AWS has to offer, and then they want to move to Azure, and then they figure out, oops, I've locked myself into the Amazon infrastructure. So it's important to be able to move your workloads across these clouds. Per workload optimization, obviously, again, declarative intent. I don't need compression because I'm storing images, or I want to have this, I want to have that, you name it. So a little bit zooming in how this looks. So if you put this in perspective, you have the application which has a persistent volume claim, and we basically insert the logic that makes that data persistent. On the right-hand side, we zoom in a little bit, and we'll go over the details as to what they mean. But the general idea is that, that we're like, everybody gets its own storage controller, and everybody is happy, to sort of speak. So, as I mentioned, Kubernetes is an integral part of our solution, and we did not want to integrate but build on top. A lot of storage solutions, through CSI, and there was a talk about this yesterday, they basically, through a plugin, duct tape their storage system and make it available into Kubernetes. But you lose all the flexibility and the mobility if you do that. So we use the operator framework in the Kubernetes native API to construct a storage control plane, because after all, there is no storage controller that we can talk to, right? All that lives in the containers themselves. And we use a thing called CRDs, custom resources. Doesn't really matter, but it's basically a value that you can put a callback on. If it changes, you execute some logic. So you can do things like failover and failure detection like that. We obviously also need to keep track of allocation, the status, the usual things that you need to do in a storage system. Another part that is very important is the node device manager. It kind of gets, since we're here in SNIA event, it kind of looks like redfish, swordfish type like inventory management. But it is important to figure out where you put your data and these type of things, what devices are available, what type of storage pools and classes you want to have and build using this information. The other part is visual topology and end-to-end testing, which is a tool that we developed out of a necessity, because how do I verify that my workload that runs on my storage system actually works on this persistent cloud storage system, right? So we needed to verify that. And all of these pieces themselves, by the way, are microservices again, right? So we really use the microservice paradigm when building these type of systems. So a little bit more of how this works. So when a developer writes something, I want a persistent volume and yada, 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 that basically eventually gets executed and sent to the Kubernetes server, where the Kubernetes server or the controller basically does an upcall to the openEBS provisioner. And this is where we inflate the volume that says how big it should be and whatnot. We inflate that to a set of microservices, right? So that's basically, there's a lot more to it, obviously. It also depends on what type of storage you are actually using. But in a nutshell, this is what it is. Visualization, so this is WeaveScope. It has nothing to do with openEBS itself, but we contributed some code to it that allows you to see the topology, let's say, of your microservice and how it is connected to storage. So you could say that it's kind of like a server enclosure management for the cloud, but not really, but you get the idea. So the other thing I mentioned is BlueGreen Deployment. So what that means, and I've put a little star at the Kubernetes service, and I need to explain this a little bit. So a service is basically the thing that you connect to when you talk to a service that runs in the cloud. And it is this service that routes your request to the right container, right? And I'll come back to this later, but it is important to note that you basically talk to the service, and the service knows, hey, this request needs to go to this microservice. And By default, these services are very simple IP tables. So we really don't want to do that in storage, obviously, so I'll get back to that. But the idea is that if I want to upgrade, let's say, the controller that is on version 1.2, I spin up this new version of that container, and then I basically swap it in and out. So you can do online rolling upgrades, and this is what they call blue-green, because if it starts to fail, I swap it back, right? It's a very simple model, actually, and kind of makes sense. And it's compared to the more traditional failover of two heads doing SCSI reservations and importing the devices and things like that. So, and based on these services, a lot of other companies spun up Istio, so you may want to look into that Linkerd that basically augment what the default service from Kubernetes does at a generic service level. But we do this at storage level, and instead of calling it a service mesh, we call it a data mesh. Because imagine that these nodes that are one way or the other talking to each other. A container attached volume is a service consisting out of a controller and a replica somewhere. You don't know where it is. You don't really care either. So there's this list from Mr. Peter Deutsch, if I pronounce his name correct, the fallacies of distributed computing. I basically condensed it to the only constant is change. So what we need to do is dynamically reconfigure and find the optimal path between these microservices that process your storage I/O. So rescheduling is one thing. Kubernetes will, without a doubt, stop your controller and spin it up somewhere else. And so you need to handle these type of situations. Transient failures, so for example, a node has some issues connecting to the network or whatever, you really want to make sure that you detect those and can act on these type of issues. And default Kubernetes services don't provide any functionality like that. The other thing is that you don't know if you're dealing with a VM or bare metal. And it is really, really important to figure out what type of connections I could use. So, for example, there is this project from Intel called Clear Containers. I think it's now called Kata Containers. Doesn't really matter. But it's basically a stripped-down hypervisor, and you only run your container in that VM. So it won't allow you to run Windows or anything like that, but just allows you to start up a small binary, and that then could connect with Virtio, let's say, right? So you need to know all this. So dynamic reconfiguration, really integral, important part. So how does this look? And this is a little bit of an example that I put up on the slide to hope to make the point across. So you have this. So the developer doesn't write this. So on the right-hand side, that's the YAML that defines how I want to connect, ideally, my controller and my replicas or my application or whatever it is. And the developer doesn't have to write all of these things every time that he wants to use a volume. These get pooled in storage classes and whatsoever. So this gets set up once, and you basically pick a class, and then you get these type of features. So the connection types in the state are reflected in Kubernetes itself through those CRDs. So you can actually observe, hey, my controller at this point is using NVMe over Fabric to talk to the other systems. So iSCSI, NBD, encryption, also very important in the cloud. Kubernetes has these constructs of Kubernetes secrets where they can store keys. So we can use Kubernetes to grab those keys and encrypt the data as it goes over the wire, which obviously is an integral part of public clouds. So to put it in a little bit more perspective, a very, very simple example. So imagine that this is the case. I have two nodes. The controller is spun up in one node, and the replica or the target needs to be on the other node. So how do we find each other? We do not want to put all the logic of the controller and the replica being able to find one another in the code. That would make it very, very difficult, right? Because the permutations are limitless. And so basically what it does is that it contacts the service mesh, which is an integral part of the openEBS operator, and says, I need to connect to this thing, but I don't know how I can connect to it because, how should I know? So then the operator talks to the node where the replica needs to be. It says, well, based on what I found through the node device manager, you should be able to, in this case, for example, spin up an iSCSI target, and then the replica says, okay, I'm done, you can move on. And then the other side opens the initiator, and then a data path exists, and we can actually transfer data. I couldn't find a faster car than this, but it's besides the point. So, you know, so why is this? I mean, this is a very simple example, right? But imagine that in the case of that this replica was on the same node. At this point, I would not want to use NVMe or NVMe over Fabric or something like that, but I probably want to stick to Virtio, for example. It depends, of course, but you get the idea, right? Because this can change at any given point in time. So the idea is that, you know, storage just fades away as a concern from the developer perspective, and the developer can focus on developing applications, and the storage admin can go back and do whatever he was doing without worrying about all the demands that the developer has for a particular workload. So let's talk a little bit about the implementation. So as I mentioned, you know, we started this out as, you know, is it feasible? So we have several data engines, as we call it. Jiva was the first one. It's basically the primordial soup that we use to figure out, does this actually stick and fly? So, you know, throw it against the wall and see if it sticks idea. And it actually turns out that people are actually really liking the fact that how easy it is. It is really easy to set up. You don't have to do anything. You just define that you want a volume, and boom, off you go. And it's also very instrumental for us to find, you know, cloud-native use cases. As I mentioned, it's just a microservice, so we can, you know, plug these things in and out. The biggest problem, however, for us to solve at this point, or at that point, was, okay, how do we do user space I/O? Because the user space I/O is not necessarily for us for performance, even though that's a nice bonus. But the problem is that on public clouds, you have different kernels, and you don't really want to taint the kernel. If you spin up a GKE instance, you get a very minimalistic kernel, and they removed all the drivers. There is no iSCSI initiator, for example, so that it's a big problem, right? So we basically said, okay, well, not just, it's a lot of work, but we'll just do it in user space. And obviously, the tainting is something that you also don't want to get into, because, you know, will Red Hat actually help you if you have a kernel panic and they see that you tainted the kernel with your own kernel module. So that was another reason to do that. Also, a side note, and maybe this is a surprise, I don't know. Performance in the public cloud is not yet the biggest concern. So, you know, very low microsecond latency workloads you don't see in the cloud yet. I'm pretty sure that will come, but as of today, that's not really necessary. So we don't need 10 million IOPS for a particular workload, let's say. In any case, to do this I/O in user space, we thought of this idea of an input-output container, IOC for short. The idea was based on observing patterns in Kubernetes itself, where you basically come to the conclusion that you have these microservices that constantly talk to one another. So instead of doing I/O through the kernel, why don't we do I/O through microservices like, you know, they seem to do all the time? Again, the Node Device Manager, instrumental here to figure out, you know, what type of devices do I want to use, what type of devices can I use. And the IOC is a daemon set, which is another construct of Kubernetes that spins up on all the nodes that you select through label selectors, but you can forget about that. The thing is that the daemon set is actually grabbing the devices and making them available through the different type of fabrics that you want to support. So iSCSI, NVMe, network block device, whatever. This is based on SPDK. I won't go into SPDK. It's been talked about a lot. You either love it or hate it, I suppose. But the general idea is that it uses user space I/O to DMA straight into the device by leveraging huge pages. So you don't necessarily have to do this with SPDK. There are other frameworks out there that more or less do the same. So this is not a logical diagram, but basically visualize how everything connects together. So you have the IOC that has ownership of the devices. There is a sidecar container, which is another pattern. You can forget about that, but this basically allows us to interact with it. The data mesh that talks to the target and the replica in this particular case so that they can find each other, and I/O completely flows in user space, obviously except for network I/O, which we have tried as well. But I'll come back to that a little bit later. So the other thing is that we did is that's, okay, so what if we could do Virtio straight from the container? So a lot of applications are getting rebuilt, and would it not be easy or cool or nice or whatever you want to call it if I, instead of calling io.read or io.write or whatever language you're using, is that the implementation actually uses Virtio in the backend, right? So instead of going through a block device, you actually use Virtio directly. So we implemented this, and it's kind of like a cloud-native I/O SDK, perhaps, if you want to call it that. We implemented SCSI in block, available in Go, because that is a lot of the languages. That's the language that is used a lot in the cloud-native landscape. And the primary reason is that I think that there is this notion of if persistent DIMMs and whatever you want to call it are so fast, why do we need file system abstractions to begin with? Why won't I just use my database and write to the device directly, right? So, but there was no libvirtio, unfortunately, so we created one. So we did a small test, SPDK in full pulling mode. SPDK comes with a FIO plugin. So what we did is we developed this Virtio library, developed this Virtio FIO plugin, and then wanted to use Virtio to do SPDK, which constructed our IOC. So we had some expectations. I think it's always good for when you do an experiment to figure out what you more or less can expect. We expected that performance would drop because SPDK uses pull mode drivers that constantly loop in a tight loop to figure out if there's work to do. We did not want to do that because if we would do that, all the containers that would use openEBS would spin 100% CPU and nobody would be looking into us. So that was not an option. So we used EventFD. Was an interesting syscall. Never heard of it because I came from a different platform. But anyways. We expected that the result was roughly around what the kernel would do on this device, and it's a little bit of quid pro quo, right? We were okay with dropping, let's say, 20% performance if it actually worked. So the results initially were not that good. For SPDK, yes. For us, no. So 490,000 IOPS, and the kernel was close to that, but we did not get anywhere near. So we looked into adaptive and hybrid pulling. Adaptive pulling is what's it called in the QEMU space. Hybrid pulling is what the kernel actually calls it. And we started to play with this adaptive pulling. So if there is a lot of work to do, we do a lot of work. If there's not so much work to do, we sleep a little bit, let's say. So this has an impact on latency, so it's configurable in a sense. But after, once we reached the 5 millisecond sleep time, we basically got results that actually outperformed the kernel as well. So we were pretty pleased with that, and that basically allowed us to continue and explore other possibilities using this methodology. So yeah, okay, I went through this a little bit already, but so SPDK can outperform the kernel, but again, this was not our goal. Our goal was to do storage in containers, and because of that, we have to be in user space. So it's feasible to do. This EventFD thing, it has a huge impact on performance. I was actually stunned to see by how much. This was around the time frame of Spectre and Meltdown, so I don't know if I had a kernel that had a partial fix or whatever, but I was surprised to see that. And basically the lesson that we learned in general is that we need to implement an I/O path that is single-threaded and lockless, right? So you can do complete asynchronous I/O without any blocking syscalls, and process all the I/O that way, and that basically gives the best results. So other things that we looked into, because obviously not everybody will rewrite their application using Virtio or whatever protocol that emerges or SDK emerges as the standard. So we have support for iSCSI, NBD, TCMU, which is a subsystem in the Linux kernel that basically memory maps the SCSI commands into this user space I/O register that you then can read and process the I/O. But to really keep up with the low latency devices, we really need to move to things like NVMe over Fabric and whatnot. As I mentioned, we also looked into networking. So if we switch to iSCSI, let's say, then we're in user space, but then we would still break into the kernel to do TCP/IP. So VPP VCL is a BSD socket-ish type-like system, and it's basically almost the same, but it is like SPDK for networking. So DPDK obviously is for networking, but it doesn't provide like a full-blown TCP stack, right? So it has packet processing, but not so much for TCP. So we started to do another experiment where we basically replaced all the socket calls and all the read calls where appropriate to use the VPP VCL calls, and we saw a huge increase because of that. Now I still have to say that this increase might also be actually due to the poor quality of that code in that time frame. But it did dramatically increase the performance. The downside of this is that, like SPDK and DPDK and thus also VPP VCL, they require their own core. So then we at least needed 2 cores to do this full pulling mode, and that didn't really look like an option. So at this point, we stepped away from that. But if we ever encounter a situation where people really, really want to do it, it's available. The other thing is I found that recently a couple of months ago, is Microsoft FreeFlow. It basically does the same thing as VPP VCL, but uses a different approach. But one thing that these things have in common is that they use the LD preload trick. Some call it a hack. I think it's an elegant solution. But anyway, to intercept the syscalls and then offload it to whatever their implementation was. And that brings me to one of my last slides, actually, is that we get a lot of questions from people who say, hey, I want to do file. Well, no, we do block. Yeah, but I want to do the same thing with file. And the problem there, obviously, is that you pull in the whole file system, this whole latency, and there's been a lot of talks already about barriers in file systems and so forth. So we know what these problems are, so I'll skip over them. But the idea here is that you could use the same approach with an LD preload trick where you basically intercept the read and write calls. And for databases, this is actually very feasible because the thing is that because it's in a container, it's a very isolated environment. So the developer clearly controls exactly how this system works. And these write-ahead logging and these compactions, they are very typical I/O patterns. So you don't have to implement all the things that you could do on a file system. So the library is mounted in a namespace, and that's propagated into the kernel. They call this mount propagation. And then you could actually do I/O, intercept the things there, and put it over the wire, for example, over Virtio or something else. Yeah, so the other thing is CI/CD testing, so end-to-end testing if you want to do this. This is, again, what we refer to as litmus. So yeah, that's basically, I think, roughly it from this slide. So summary, so what we try to do with openEBS is bring advanced storage features to individual container workloads, cloud native, not cloud washed, and using the same paradigms that these developers are accustomed to, so it feels like a natural fit for them. The other thing is that we do I/O handling in IOC, control release cadence. Again, that's the most important thing for us. We want to be able to upgrade the I/O path if we see fit and not reboot the kernel or patch the kernel or things like that. A declarative provisioning and protection policies. Obviously, if you do storage, you want to have a form of backup. No matter how cloudish you are, always make sure you have a backup. Remove the friction between teams. Multi-cloud from public to private and vice versa. And as I mentioned, it's not a scale-out storage system, but it's yes. So with that, are there any questions? Okay, well, thank you for your time, and enjoy the conference.